Students, good morning. I am so happy to see you once again through CETEL YouTube channel. Today, I am going to provide a brief information on units and dimensions. Significance of units and dimensions. Why the knowledge on units and dimensions is essential for thermodynamic calculations. Units and dimensions play an important role in understanding various physical quantities involved in thermodynamic calculations. This knowledge, the knowledge on units and dimensions are essential or an important in understanding various physical quantities involved in thermodynamic calculations. The physical quantities are used to define or describe. The physical quantities are used to define or describe very precisely various laws, natural processes, and phenomena. So physical quantities, understanding of physical quantities is essential to describe various laws, natural processes and phenomena. These physical quantities are characterized by dimensions. Dimensions such as mass, length, time, temperature, area, volume, density, force, pressure, energy, heat, work and power. What I am trying to say is, dimensions are nothing but characterization of physical quantities. Dimensions are characterization of physical quantity. The magnitude of dimensions are known as units. Units are nothing but magnitude of dimensions are known as units. Clear? The knowledge of units and dimensions are essential in order to define various physical quantities involved in thermodynamic calculations. Physical quantities are essential used to describe the various laws, natural process and phenomena. The physical quantities are characterized by dimensions such as mass, length, time, temperature, area, volume, density, force, pressure, energy, power, heat, work, etc. etc. The dimensions, magnitude of dimensions are known as units. The dimensions of any system or property are divided into two categories. One is primary dimension. Another one is secondary dimension. Clear? Magnitude of dimensions are called as units. This is the brief information regarding the significance of units and dimensions. Let us see one by one very precisely: force, pressure, energy, work, heat, power along with its units. Now I am going to discuss the dimensions along with its units. First one is force. Force is the product of mass into acceleration. Force is nothing but, or it is defined as the product of mass and acceleration. Force is equal to mass into acceleration. This definition is arrived from Newton's second law of motion. Newton's second law of motion. Newton's second law of motion says that force is defined as the product of mass and acceleration. Then what about Newton's first law of motion? Can any one of you able to say what is Newton's first law of motion? It is very simple. Newton's first law of motion says that a body at rest will remain at rest. A body in motion will move continuously with an uniform speed in a straight line unless acted upon by an external unbalanced force. This is Newton's first law. Newton's second law, force is the product of mass and acceleration. Newton's third law deals action and reaction. For every action, there will be an equal and opposite reaction. Give it such things. Force is nothing but product of mass and acceleration. F is equal to m into a. M stands for mass, the unit is kg, acceleration is meter per second square. In SI units, system international or international system of units, the unit for force is Newton. The unit for force is Newton. Notation for force is N. So 1 N is equal to 1 kg meter per second square. The dimension is force, unit of force is 1 Newton. 1 Newton is equal to 1 kg meter per second square. What next? Pressure. Pressure is nothing but, it is a actual force. Pressure is nothing but, or it is defined as the normal force. Normal force exerted by a fluid. Exerted by a fluid per unit cross sectional area. So force, pressure P is equal to F divided by A. Force per unit area. Clear? Force, the unit of force is Newton N. Unit of area is meter square. So the unit of pressure is Newton per meter square. In SI units, international system of units, pressure is represented in terms of Pascal. Pascal. The abbreviated form is PA. So 1 Pascal is equal to 1 Newton per meter square. 1 Pascal is equal to 1 Newton per meter square. We can see more number of units for pressure. 1 bar. 1 bar is equal to 10 to the power of 5 Pascal. Or 1 bar is equal to 10 to the power of 5 Newton per meter square. 1 bar is equal to 0.9867 atmosphere, or 1 atmosphere is equal to 1.01325 Pascal. Hence 1 atmosphere is equal to this is bar, 1.01325 into 10 to the power of 5 Pascal, or 1.01325 into 10 to the power of 5 Newton per meter square. Or 1 atmosphere is equal to 760 millimeter mercury, or 29.92 inch mercury, or 702.1 inch water. So these are all the units frequently used in estimation of pressure in thermodynamic calculation over force and pressure. What next? Another one is energy. Energy is energy which can be converted into work, or it can be produced from work. Energy can be converted or transformed into work, or it can be produced from work. Transformed into work, or it can be produced from work. Clear? Fortunately, energy has the capacity of producing effect. Energy has the capacity of producing effect. Energy in the form of heat and work. Energy in the form of heat and work can be exchanged between system and surrounding. First point, energy is an important thermodynamic property. Which can be transformed into work, or which can be produced from work. Energy is an important thermodynamic property which can be transformed into work, or it can be produced from work. Fortunately, it has the capacity of producing effect. Energy in the form of heat and work can be exchanged between system and surrounding. This is the brief information regarding energy. Energy available in many forms. Say for example, chemical energy, mechanical energy, electrical energy, electrochemical energy, electromagnetic energy, electrochemical, internal energy in many forms. Whatever may be the forms, it is shortened only two different forms. One is macroscopic energy, another one is microscopic energy. In macroscopic energy possessed by the system with respect to external reference plane. Energy possessed by the system with respect to external reference plane. That means kinetic energy, potential energy. You might be studied in your school days itself. Kinetic energy is nothing but half mv square, and the potential energy is equal to mgz. So macroscopic form of energy means energy possessed by the system with respect to external reference plane. Microscopic energy means internal energy. Internal energy is nothing but energy possessed by the system inherently, or energy possessed by the system due to the configuration of atomic structure or molecular structure. Clear? Internal energy notation is U. Internal energy notation is U. So total energy of a system is sum of kinetic energy, potential energy and internal energy. Total energy of a system E is equal to sum of kinetic energy, potential energy plus internal energy. Clear? Okay? Right. For a system, if energy performs certain amount of positive work, its surroundings will perform an equal amount of negative work. Hence, total energy of the system is constant or zero. Changes in total energy of the system is zero, because law of conservation of energy says that the total energy in the universe is constant. energy can be transformed from one form to another form. There will be a deletion or production. Clear? So total energy of the system is constant. Changes in energy become zero. This is the brief information regarding energy. What next? Work. Next one is work. Work. Both work and heat, they are energy in transit. Both work and heat are energy in transit. Energy in transit, or you can say that work is a form of energy. Work is a form of energy. It is defined as the product of force and displacement in the direction of force applied. Work dW is equal to F into dL. In actual or perfect form, you can write like this: dou W is equal to F into dou L. Why I am writing this partial differential means work is a path function. You please remember the information. Work is a path function. Work is a path function. Moreover, it is inexact differential. Inexact differential means while you calculate the amount of work done, you cannot include initial work and final work. You cannot go and take the difference between initial work and final work, because amount of work done depends on its path in which it is produced. It is a path function. Please remember, work is a path function, hence it is inexact differential. So you can write like this: dou W is equal to F into dL. In differential form, I am writing dW is equal to F into dL. Okay. Force is nothing but pressure into area. So dW is equal to pressure into area. The displacement dl is nothing but changes in volume with respect to cross section area. So dV divided by A gets cancelled. So dW is equal to P into dV, or you can write like this: W is equal to P integral V1 to V2 into dV. This is the mathematical representation of amount of work done. If the value, calculated value, if it is positive, W is positive, it means this is work done by the system. Work done by the system. Work done by the system means it is a expansion process. The process belongs to expansion. When you calculate W, if the W value is positive, it means that work done by the system. The process becomes expansion. If W is negative, work done on the system. Work done on the system. Work done on the system. Work done on the system means the process becomes compression process. When W is equal to minus value, the process becomes compression of gas. If positive, expansion process. If negative, it is a compression process. Clear? Right. This is the sign convention, very much important. Clear? Okay, what next? Next one is heat. Heat, again, heat is a form of energy. Heat is the form of energy. I am already telling you that both heat and work are energy in transit. Heat and work are forms of energy. Heat is nothing but, consider a system, it is separated from its surrounding by a rigid boundary. If the difference in temperature existed between system and surrounding, obviously heat will flow from a region of higher temperature to lower temperature. This heat flow will be stopped when difference becomes zero. Clear? This is the brief information regarding heat. Modes of heat transfer is there. Modes of heat transfer, conduction, convection, radiation, something like that. We'll give it to you. Right. Coming to the point of work. What is the unit? This is the dimension. The unit becomes, for force, this is Newton. Distance is meter. So 1 Newton meter. Newton meter is the unit of force. In system, in SI units, international system of units, the unit for force is calories or joules. 1 joule is equal to 1 Newton meter. 1 calories is equal to 4.184 joules. Similarly for heat again the energy unit 1 joules is equal to 1 Newton meter, or 1 calories is equal to 4.184 joules. This is the brief information regarding the significance of units and dimensions. This knowledge is very much essential in order to understand the physical quantities involved in thermodynamic properties. Essential physical quantities are frequently used physical quantities in thermodynamic calculation is force, pressure, energy. In energy, work and heat, another one is power. Power is amount of work done per unit time. Power. Again, power is equal to amount of work done per unit time. That means in work done, this is joules, time for seconds, 1 joules per second. 1 joules per second is equal to 1 watt. 1 joules per second is equal to 1 watt. The famous unit for work done is horsepower. Horsepower. That means 1 HP is equal to 745.7 watts. So, important physical quantities are force, pressure, energy, work, heat and power. This is the brief information regarding units and dimensions. Thank you.